Hello everyone, welcome to another stream. How's it going? How's it going? Oh. Right, so it's been like a week since well, yeah, it's been over a week since I last streamed. So, last week, we were trying to get this, um, we want to try and construct a BVH on the GPU, but knowing if the code is correct is very difficult. So we're currently running it on CPU, and we're debug drawing the tree based on a number of leaves. But this is not the BVH construction code. This is simply going over and just attaching children to parents in a very simple way. But we need to actually implement the proper algorithm. Hey, Eustace, thank you so much for the sub. Really appreciate it. How have you been? Thank you, sir. So we started wiring it up end of last stream, the actual implementation. And I realized when I finished the stream what the problem was. It's because we're not sorting our molten codes. So each leaf node has a molten code. It's basically, yeah, you can search up if you want to know what a molten code is. It's in this paper, or in this blog, I think. Yeah, molten Z curve. So it's a 1D coordinate which maps to 3D space in the form of Z shapes. So there's a micro Z, and then there's a macro Z, and there's even more macro Z. Like, there's just levels to it. So if you sort something in, if you convert a 3D coordinate to a Morton code, it's a 1D coordinate which you can fit into an array. But it also means that stuff close to each other in a 1D coordinate would be close in 3D space. Yeah, so I wasn't sorting these, and that was the issue. I need to sort them. Doing alright, how am I doing? Yeah, not bad. A little tired. I'm still recovering from going to work last week because last Tuesday there was like a party, and we stayed up late drinking. Then I had work the next 2 days after that. So yeah, I was kind of shattered by the weekend. But yeah, it's been like really busy as well. Trying to get the wife's car sorted. So it's now past the MOT now, but we had to get some wheels replaced and really clean up the lights at the front, because the lights were very, they're very sort of like very stained. I had to clear the stains off because yeah. So I was sanding that down at the weekend. But yeah, things are all passed now, which is good. So yeah, just trying to get my head back into this really. Yeah, so randomly generate some Morton codes. Where's the randoms? Ah, the rand. Right. Yeah, this will randomly generate the So this randomly generates a bunch of Morton codes, but we need to sort them. We need to sort the nodes. So I think what we're better off doing set internal nodes. So these are not the leaf nodes, right? Internal nodes to have Morton code equals 0. Then I think we want to randomly generate leaf nodes, right? Randomly generate leaf node Morton codes. Then we want to sort them. Yeah, let's bring back sorted mate. So I think it's const void A, const void B. So I think if you want to sort from low to high, it's basically B take A. Yeah, we need to do some. Right, so where we set that Morton code to 0. Yeah. So after we've done these, we need to sort. So we queue sort base address, which is leaf nodes. And then we want to number of members. That's next. The number of members is, I think, 256. Wait. Leaf node count. Size of E32. And then the compare function. So that was sorted, mate. Right, and then we'll sort the Morton codes low to high. So that's a key part of how this works, because it assumes that all the leaf nodes are sorted from low to high in that Morton code space. So all of the nodes that are next to each other are near each other in 3D space. And then we're going to go over and then assign it to that node structure. Yeah, this is very thrown together. Like this node is like, it's not gonna be what a GPU node looks like, but it's got a range of nodes that it can see. So if it's very high up, it views a whole. So what's the range of leaf nodes? What's the range of its descendants? And this is the direct children, the depth, parent index, and the Morton code. But yeah, we'll. So what's different about this BVH compared to what this blog is doing and the paper that is linked to it? I'll drop this in the chat again. Is this the paper assumes that it's a BVH with 2 children. Each node has 2 children. If it has, yeah. So the one that we're doing has 2, 3, or 4. So it's up to 4 children. So where's the paper that it links to? I think it's this one. So this paper and this blog is about building this BVH node in a highly parallel manner on the GPU. Um, yeah, close that one. Right, so now that we've set up those leaf nodes, those Morton codes, in our debug view, we should be able to see them at least be sorted. Right, so I gotta figure out. Right, let's start simple. So again, this is not me building the BVH tree because this is what we want it to look like when I've when it works, right? We want it to look like this. I've built it in such a simple way on the CPU side, but I'm trying to build another version which builds it and will produce the same result or a similar result. Everything will be attached. All the nodes will be attached, but there won't be it might be more balanced or something. I don't know. So the problem with this, so this is the Morton code. Is it low to high? I forget how I'm displaying this. Am I displaying at least significant bit to most significant bit? Let me just figure that one out. I don't think it is. Um, hmm. Right, so where am I rendering? It's no drawer, isn't it? It's just a bunch of... Right, here we go. So we're taking the... Oh boy. What bits are we displaying first? So it's in an inverse. So it's most significant bit first. Right. Good to know. So most significant bit first. So these don't look sorted. Maybe. Right, I think they're high to low. Because that one's showing up here. And then... Yeah, then this, yeah. So I think they're sorted from high to low. Let's quickly Google sort. Enhance. The idea is to assign Morton code for each primitive, sort the Morton codes, and generate. The sorting effectively groups the primitives so that one's close to each other in 3D end up close to each other in a resulting tree. It doesn't specify high to low or low to high, I guess. Yeah, we should probably I want to make it low to high though. Let me just invert that the other way around. Sort it, mate. Alright, let's try that. Alright, so these are the most significant bits first, right? Those just, yes, put it the other way around. Sweet. Yeah, that's good. So now the next thing to do is to make, so we're going to still debug visualize it like this, but we're going to be paying more close attention to the console output because, so the problem is my debug tree, the visualization isn't great for partially correct data. It has to be a fully working tree. Why does it have to be a fully working tree? Yeah, you'd have nodes missing. But yeah, I think we're going to toggle between. Yeah, we're going to have a full. Yeah, right now I haven't got the implementation of the paper written up fully yet. So we can't plug it into rendering these to linking up the tree correctly. This is just a very simple version. So just me paying attention to the output here and just trying to reason about the output at a very small scale, and then we can move on to the next part of it. So let's just go into the actual. So the bit that we started implementing in the last stream is this determine range thing. Here, this is a good image. Hey, Petra Fatos. No, this is so it's a binary tree. The paper is saying a binary tree. We want to make a tree with 4 children. So we can basically take so effectively the first part of the algorithm. So these are the leaf nodes, right? These orange ones are what's known as the internal nodes. So for us, what we would like to do is essentially get rid of this layer here, this 1, 2, 5, and 6, and just have 3 and 4. So this would just be renamed to 1 and 2. And then 1 will have these 4 children, and 2 will have these 4 children. So we could essentially run the algorithm in a granular way first, and just build a binary tree, and then I can just delete every other. I can join 2 siblings together, right, and make another tree. That is the method I will probably go if I can't get it to work from the if I can't get it to work all in one go. So effectively, this binary tree, the way they do it is each thread gets a node, and each thread is able to say 1 will start searching here where 1 is. Based on the Morton code bits, it knows how to sort of start searching to the left or the right. In this case, it'll go to the left, and it'll stop here because it's at the end. But it can determine the range of nodes that it will see. And this is the determine range thing that we're trying to calculate. 3 here, it knows that it will start searching. Is it a 3? I forget these. Yeah, maybe it starts searching at 3. And based on the Morton code bits, it knows, hey, I need to start searching to the right or to the left. And then search the left in this case. And then it produces this range from 0 to 3. This is the code that we're trying to, we started writing last time, but I didn't quite get a correct result. So I'm just trying to see, this is the terminal output here. These are the ranges of the nodes, of the internal nodes. So here we're getting 0 to 8, 3 to 8, and then 6 to 5. That one's a bit odd, isn't it? Obviously it needs to go low to high, or be the same, I think. Yeah, it is going to be a bit of a booger. So obviously we have 0, 0 to 3, that works fine. But yeah, 0 is always going to work fine. There's a special if statement for 0, internal node 0. So for 1, so leaf nodes 3 to 2. That's way wrong. So, right, let's get back in there. And all right. So here's that determine range code. Where is it? Here it is. So this is like in a function. Right. So it ends up doing like a little binary search thing. And the print is here for the range. So there's an implementation of it on GitHub here, which we started taking a look into. So how long is it again? Right. So the issue is times 3 take 1, isn't it? So we've got to convert it from. So the issue is we need to go from an internal node index into a leaf node to where we start searching. Yeah, there's a few things that's clearly wrong. Yeah, so we've changed this to try and make it work with this. Is it called a quaternary tree? How do you say that? Quaternary. No, that ain't it. So you've got binary, trinary, quaternary. Right. Quaternary. Right. A quaternary tree, is that how you say it? That's a quad tree, maybe. Alright. Yeah, so because we've got a quad tree instead of a binary tree, we've got to slightly change the logic. So I'm trying to make it such that it's called a quad tree. Yeah, it makes sense, doesn't it? Yeah, sort of, mate. It's the way the English sort. You know. Yeah, it's very easy to overcomplicate. It's just quad tree, mate. That's cool. Welcome, Taz. Welcome, Double Truth. How you guys doing? Yeah, so the way you could think about it is that yes. So I'm basically trying to make it an even number and group 2 bits at a time. The binary tree one just looks at a single bit because you obviously get 2 states. And that's how it. But I'm trying to make sure that this quad tree one looks at 2 bits instead. So maybe that's causing a bit of an issue. You know, maybe I should. So that's how the binary tree one works. So I'm just trying to remove the odd bit, right? And then the other thing is we convert. The way the binary tree one will work is we'll take the internal node index and just use that as the start and leaf node index to search. So 3 will start from here in the leaf node. The internal node will start here and then start doing this sort of search for where the start is. So if we are to say this will be 0, that would be 1. And if we do 1 times 3, it'll end up here. That's correct. But if this is 2, right, this will be 2 instead because we're getting rid of these children nodes here. Because 1 will take 4 nodes and this one here will be 2 and it takes these 4 nodes. So this will be 2. And if you times it by 3, you're obviously going to get 6. Now that's going to be wrong. Right. So it's as if... So how did I generate calculate the number of leaf nodes again? Here it is, this divide round up thing. So I think it's something like this, where we need to do like a take 1 times 3 or something. Yeah, I need to figure that one out. So obviously if this is 1, 1 times 3 will be put here. And that's correct. But if this is 2... Oh no, wait. This code, the way the binary tree one works is it will say this is 4. So I'll start searching at leaf node 4. So these need to be next to each other, right? And then that will go and search across there. Okay. So if I were to say this is 1 times 3, okay. Or I could say 1 take 1 times 3 plus 3. I don't know. Let's see if that will work. 2 take 1 times 3. Put you at 3. Then plus 3 put you over 6. That ain't right. So you somehow get 4. Yeah, so I guess the sort of sequence I'm trying to look for is... So let's just write the sequence and then we can work out what we need to get. So the first one will be 3, next one will be 4, the next one will be... Or is that always going to be the way it is? So yeah, internal node 1 will map to 3. Let's write the other way. 1 will map to 3. 2 will map to 4. Will it always be that way? Yeah, because then you have 1, then 2, then 3, then 4. Oh no, you went, sorry, 1, 2, 3, 4. Right, I think I need to draw out an actual tree so I can understand it. So we need to draw out 16. Yeah, we draw out 16 nodes. Right, 4, 6, sorry, 4, 8, 12. Right, so when we refer into, let's just put hard lines in between here so we can see 4s. Right, cool. So basically these guys get a parent, right? Like so. These guys get a parent, like so. These guys get a parent, like so. And you guessed it, these guys get a parent, like so. So then, I guess you just have a 1 node, or maybe 16 was a poor choice. Maybe you need to go higher, but let's just start here and see what we can figure out. All right, so this is the tree. Where it's got another layer other than just, you know, because we was just thinking about this case where this is 1, this is 2. Oh no, we are thinking. So yeah, so this would be internal node 0, 1, 2, 3, 4, 5, 6, 7, right? So this would be internal, I guess it's still kind of similar. 1, 2, 3, 4. This would be internal node 0. So I guess in this case, it's still the same sort of thing. You want this one start looking here, this one start looking there. What does it matter? Hmm. So yeah, I guess you'd say that's 3, 4, and 7, 8. Yeah, we can try this sequence, right? But then how does the binary node 1 work when you've got another layer? So 1 will start searching here and it'll just go there. 2 will start searching there and it'll just go there. 3, it'll go across all of those, right? 4, go across all of these. 5. Right. I guess we can try. So then 3 will map to 7. 4 will map to 8. That's just a times by 2. This is just a times by 2. Times 2 plus 1. Times 2 plus 1. So the logic could be yes, if it's odd. If it's odd, it's times 2 plus 1. Let's just try this out. It's times 2 plus 1. If not, it's just times 2. Right. So I guess you would just do that, right? I'll make it the branchless version. So if we take a look at that, so we haven't changed that common upper bits function. Let's just take a look at the numbers. So they're the wrong way around again, but they kind of, right, so how many children? We've got 16. Right, so we're expecting, so this range, we're expecting obviously 0 to have the range of all 16 nodes, 0 to 15. That's correct. But that's a hard-coded one, very hard-coded. So we can skip that one. 1 goes from 0 to 3, that's correct. 2 goes from 4 to 0, nope. 3 goes from 5 to 7, that's a big no. Right, so I think this is because we've not changed that common upper bits thing. Because this is the same for the binary tree one. I wanted to say, remove the odd bit from this result here. So this is basically taking 2 Morton codes, XORing them together, and finding. So an XOR is basically a not equal for every single bit. So it's doing a not equal, and so if it's not equal to the other one, then it puts a 1. If it is equal, then it puts a 0. So and there's a count leading 0, so it gives you an index based on where's the closest difference in the bits. So we're making it even, always even. So essentially like grouping 2 bits together. So the binary tree one just needs 1 bit because it's got 2 states, but I think we can just group 2 bits together and it should hopefully produce the results we're looking for. We'll find out. The ranges are going a bit backwards though. That's another thing to think about. So it's 3 to 1 this time. So that got worse. 4 to 0, that didn't change. The only one that changed was this 3 to 1. So we have the Morton codes here, which is interesting. So we could play about with that. We could specifically follow a single 1 and see what it's doing. So why don't we start there? So the one we want to know more about is internal node 1. So we're going to follow this one and see why is it doing what it's doing. So what's probably best is if we just put in one of those programmable breakpoints and just follow it through in the debugger. And this way it should be nice and easy to figure out what's going on. So taking a look at things, we've got L delta. So we're starting off at leaf node 3. So we should ideally want to start scanning to the left. So L delta is 4, right delta is 2. So this one is going to say, oh, for crying out loud, the diff is unsigned. So yeah, we should really make that a bit of signed logic. Should probably. Right, what are you doing with diff? Yeah. Times L max. All right. So let's hop back in there again and see what goes on. Right, so diff was -1, so it's saying go to the left. And then we got delta min, which is 2. Right, because I think 2 was right was 2 or something like that. Now this if statement's in here for some form of like bounds check. So we're going to go into here. Is there really a bounds check? So the temporary index to look at. Hey, random user. It's 2024 and your monitor can do more than 2 colors. Oh yeah. No, this is just the theme that we got in GF. But yeah. But I also don't really like, you know, most color schemes are kind of like, you know, too rainbowy. You know, there's just too many colors. I just quite like having a basic 2-tone color scheme, you know? Much easier. That's cool. Debuggers at GF. So it's GDB under the hood, right? But it's called. So Next makes it. He's also got a support page where you can get extra features. Hey Joe Mega, how's it going? But yeah, it's pretty decent. It's much easier than using the terminal interface, that's for sure. How's it going, Joe Mega? What have you been up to? So we pull out the Morton code and compare with the self one, right? Okay. Delta is 4. Right, so it's going to scan to the left. Right, so if that goes out of bounds, it's going to make delta -1 and not do anything. And then it's going to quit. Right. Yeah, that code can be written probably better than that. Those if statements are not, yeah, a bit weird. I feel like there's a much better way to clean that up. But yeah, so it went around once and it produced. Right, so. Right, our max is now 4. Right, interesting. Yeah, I wonder when you change that 2 to mean 4 at some point. But yeah, it's definitely interesting. So that'd be plus -1 times 4. So it'd be plus -4. I'll move it back. We might not have to change much. Right. I got another idea before I try and. So we might get away with keeping this common upper bits thing the same, but then making it jump further. Let me just try that. So if we make this 4 instead of 2. See what that output's like. No. Close though in some way. And these numbers, I would like to label these leaf nodes better because it's a bit confusing. Because the leaf node indices. Let's do that quickly. Yeah, but how do you know what leaf node index is? I don't think you know it. No, it'll be lined up correctly when we what it? Yeah, we'll do it later. Ren decided to go into something some people call insane, so I'm gonna make my own language again for the fourth time just to make my own engine in it. This is the way. Yeah, I've tried to do that a few times. Yeah. So what's happened with Rust? Does it list all the registers? I'll be doing some by hand, SimD, sometime soon. So this would be great. Yeah. Yeah, the thing is about it is I think I went from C or C++ or C, C++, C, Rust. Tried making my own languages a few times. Went back to C, and now I'm here. Yeah. So I think you might end up back on C, Jomega, maybe. You just be like, screw it, back to C. There was something I wanted in addition to what Rust had, so own language is sent to 0, right? So what exactly do you need that Rust doesn't provide? Or is there something, because what happened to me, why I stopped programming Rust, is that I felt like it was just getting in the way more often than actually helping. And the rough edges of C were actually a better problem than the Rust getting in the way of me programming, basically. Yeah, so 1 links to leaf node 0 to 3. That's correct. 2 links to 0 to 4. That is incorrect. So it went the wrong way. 3 links to leaf nodes 5 to 7, which is this 10 node here, all the way to there. So that's wrong. So it went the wrong way again. 4 starts at 8. So that is, well, it actually went 5 to 7. So it's 5 to 7. Wait, 3 got it correct. 3 got 2's 1 correct. So maybe I just start searching in a bit of a different place. Yeah, maybe. Just maybe. The answer all along is just... Wait, 1 was correct, 2 was wrong. Is it just times by 3 then? Yeah, is that right? Right, that's not good. Right, so the logic was, if you've got an internal node, which is a non-leaf node, 1, that wants to start searching at 3, 2 at 4, and then 3, and so that'd be 7, then 8. Right, so the way we sort of said it, if it was an odd number, it's times 2 plus 1, and if it's an even number, it's just times 2. Now, 3 got 2's 1 right. Is that right? Yeah, 1 was correct, 2 was wrong, 3's got 2 correct. Oh, wait a minute. So, there's a fifth one? Oh yeah, sorry, 0 is the root node, right. Yeah, 1 is correct, 2's wrong, 3 got 2's correct, and 4 is wrong. So I'm thinking it's just So we need, so the stepping logic instead will be 7, then 11. So it's multiples of 4 take 1, right? And then that'll be 15. So the logic then is always times 2. Wait. No. Yeah, times 4 take 1. So let's try that out. Alright, see what happens there. Right. Why did that one... Yeah, so the scanning is wrong. So 2 now starts at 5. Yeah, got that one a bit wrong, didn't it? Alright, was it 5 to 7? Was it doing it right? No, sorry, 3's wasn't the correct 2, was it? It's not 5 to 7. It should be 4 to 7, but it's pretty close. Hmm. There's some issue with the const generics. Can't use const context, generic parameter packs, etc. Yeah. Yeah, I think when I remember looking at Rust a while back, they seem to, their generic stuff, or templates, whatever you want to call them, were quite limiting. Yeah, you could do a lot in them, but there were certain things where it's like, yeah. I did like the whole trait thing though. You could guard well, you had to guard a generic by a trait if you wanted to. Yeah, so everything was more compile time. Doesn't seem a way to watch XMM registers, damn it. Does it list all the registers? Oh, right, sorry, you're talking about GDB, sorry. Right, I don't know. I've not tested out the SIMD stuff in GF. But if it's like GDB, then you should be able to. Strange. Also, you want some fancy enum stuff where you can do dimension 3D, right? Okay. Oh. Right, so why doesn't... So 1 is fine. Yeah, so is it this search location that is... So that's correct, isn't it? 2 times 4, 8. It's like 1. 3, yeah, I think. So this one. Yeah, so what about just times by 3? How does that look with these ranges? 6 to 7. That just ends up doing a couple of pairs. Yeah, so I think there's something more underlying that's an issue with these common upper bits thing. I think we've got to group them together a bit. Remove the odd bit. So there's a pair of bits, so there's 4 possible states. I think we've got to do something like this. Mixed with what we've been trying to mess around with. So it might be that 4 times 4 take 1. We're getting the same sorts of numbers again there. What did we try before? It was times 2 plus index if odd. Won't be everywhere, but I want to have certain places where I can have names starting with a digit. Right. Yeah, I don't know. You can get around that though, right? It's not really a reason to make a whole language, right? But yeah, I find namespaces like, they make the code harder to traverse and find, basically. You need like a full IDE that works, which in 2024 is not really a thing all the time. Yeah. Okay, so the other way. Right, let's put it back to. Let's have a think on why. So I think this is the one you want to start on because go back to that diagram. This diagram maybe. Internal node 1, 2, 3, 4. We want 1 to start here on leaf node 3, 0, 1, 2, 3, 2 to start on 4, such that we won't get any gaps. So this one will search to the right, this one searches to the left, and then this one will start here. Or will it? Yeah, this one will start here and search to the left. You gotta make sure they both search all the way properly and agree where to do the cut. If not, you'll get gaps. So I think this is the right one to do. I've just got to debug it from here. So 1 was correct. 2 was incorrect. I've got to find out why. So it starts at 4 and then it does something. So it searches the wrong way. Got to figure out why that is. So we got the bits. We can view the bits on the screen. They are here. So there's 3, there's 4. So yeah. Right, let's have a look at that. So wait, 1 is wrong again. Oh yeah, because I removed that common upper bits thing in it. Is all correct? Right, okay, so let's put if statement in. If index equal, let's do 2. The Rust box is special, right? Yeah, it's got an intrinsic, hasn't it? Where they have yeah, I think. Also want some non-fancy stuff and fancy stuff. How functions work, default values, label arguments, return names. Yeah, those are kind of nice. Because in C, you basically put stuff in structures such that you can have named parameters, isn't it? Right, so it starts at 4. There's the Morton code, which is not really readable. But hey ho, because you need to see the bit pattern. But we can see it visually in our render anyway. So we've got two, and then 1. Why does it go left? So it looked at the node before. Compute the upper bound. Right, so it jumps back by 4. And then it will go back up. Hmm. Gonna run up a spec about 1,000 lines at the moment. Awesome. Gonna make a gist of it later and probably also some feedback from people. Cool. Nice. Yeah, if you need any feedback, let me know. I can always, provide you some. But awesome. What are you just gonna use LLVM as the backend, or custom backend, or anything else? Or a C backend maybe? Right, so where to next for debugging on this thing? So we should inspect the Morton codes and see why. So it got a 2. Let's restart that. So leaf node 3 diffed with this one. Right. And then a 1. Yeah, you know what? I think I always saw our Morton codes the wrong way around. Maybe it does need to be high to low. Yeah, I think that's why. Was part of the reason why. Yeah, I think you're at high to low because... No, this one does it the other way around. Right. Yeah, I think it just might change the logic of... Alright. 3. Yeah, it's probably okay. So 1 does go to the left fine. 2 ends up going to the left and should go to the right. So open up the debugger again. Well, let's just run it for a sec. Yeah, so basically this is 3 here, this is 4. You know, when you XOR these together, right, these are not equal here. So you're going to get a 2, right? Whereas when you start searching, but when you do an XOR where these are not equal with all the bits, and do a count trading zeros, you're just going to get a 1. So when you take a difference, yeah, right. I think I got the search logic the wrong way around. That needs to be -1 then 1, I think. That didn't work. Well, I probably got changed somewhere else. Diff. From where am I? UK. To start, probably allow for different backends. Yeah, I understand. Well, that's something you want anyway, right? You always want different backends. But because one hand LLVM is nice, on the other hand, it'll become bloat. Yeah, that's correct. Now, the easiest option is just to output C code, but then, you essentially you run in 2 compilers, one after the other. But it's the option you have to go with sometimes. And yeah, LLVM, also you have to maintain it as well when you change versions. But yeah. And I've heard it's a bit of a pain because it's quite abstracted. And if you want to output a certain thing for a platform, it's quite a pain. But yeah, it does optimizations, which is kind of nice, but I guess with enough time you can always write optimizations as well. I think the sort of SSA form optimizations are not too bad to write. I think it's like when you lower it down from that SSA form into x86 bytecode or machine code, you have to write another optimizer for that level as well. So there's just like 2 levels of optimizations. Right. Let's have a bit of a gander. So we're looking at, so 4. The reason why it ends up going to the left, this is leaf node 4, 0, 1, 2, 3, 4. It XORs the right one with this one and does a count leading 0. So this is the bit that differs. And so we get a 1. Does the same here, XOR. This is the bit that differs, so we get a 2. And because the left is greater than or less than, whatever it is, it ends up going to the left. Um, so that is great. So for this Morton code here, there's not really a difference, but as I'm going to the left anyway. Right, defaults to going to the left. Um, um, yeah, what do you mean by RTTI? Like runtime type information? Do you mean like C++ RTTI, or do you mean like do you mean like just literally like type information as data? I said or. I said A or B, so I don't know what yep means. Um, so if we're doing an XOR between these two, and these differ, so I want this one to go to the right. Um, so if they're the same, we could say they go to the left. If the right, see, this one starts there, wants to go left. This one starts here, wants to go right. It's not. Yeah, I think the logic doesn't work for a quad tree. It might do though. Hmm. Type info is nice stuff like editors when change data of things like components. Yeah, that's true. It's good for like printf as well, like printing data, and yeah, going over, yeah, automatically just doing stuff based on data types, which is that can be automated. But yeah, not all things can be automated though. Sometimes they require manual code, but it's a good, yeah, it's a trade-off between compile time versus runtime performance. But it's good. So if this was a binary one, it would do an XOR. So it would start on one, look with that one, look with that one, and end up going to the left. Then for two, it would start there, do an XOR between these two, and it still would go to the left in this case. All right. Let's look at this code a bit more. Compute the upper bound for the length of the range. Right, so it's always starting from leaf node index and then working out the other end. Is that right? Have I read the code wrong? No, so it is always so whatever you work out leaf node index to be, it is always passed out as one of the starting ranges, basically. The end or the start. Okay. Right, let's just do a bit of a hack. Let's just say if it's odd, it goes left. If it's even, it goes right. And let's just see what happens there. See how it behaves. Why does 3... So it should be going to the left. Right, starts at 4, should be searching right. We should look into that. This one starts at 7. Wait. Times 2. Whereas 3 times 2 is 6. Yeah, then plus 1, 7. No, I think I got those wrong. But this ain't right. Well, you can always make him search left, I guess. But I wonder how correct that is actually going. Going up past 16 nodes, I don't think it'll be right. Yeah, so it didn't quite get to the 4 there. So there's a bit of a gap. 11 didn't even go. And this one ended up going all the way down to 5. It's a bit incorrect. Right, so let's do that other pattern that we was doing. The other pattern was internal node 1 maps to 3. Yeah, 3, 4, then 7. Wait, 7, 8 was maybe wrong. Let's run that again just quick. One starts here at 3, 2 starts at 4. 3 starts at 8, 9, 10, 11. Shoot. 11, 12, that's what I meant to do. Right. So, right, that logic was a bit wrong. So 1 times 3, I guess. Wait, you can't do dynamic libraries in Rust? Right, because the ABI is not stable? Is that why? So you have to once the ABI? Um, yeah, so that's just times. This is times 3. How would you get that? Times 4, take 1. Yeah, so I guess you'll just say if odd. Let's just try this out, see what happens. So if um so it's odd, I would like it to be times 4, take 1. And then else would be, if it's even, just do times 3. I think that there might be a simpler way to do that, but yeah, I think that's right. Wait, no. That's times 2, then this one will be times... Well, that didn't work. Neural tooling, also planning for doing code organization slightly differently. That's cool. Code organization, the organization code is a 3 levels package. Libraries and binaries, modules. A package is the main unit of distribution. Collection of libraries that can be used by other packages. A library is a piece of code that is intended to be used by other code and therefore does not produce. Meanwhile, binaries are meant to run their own code and cannot be used by other code. Modules represent individual code files that are nested. So the bit I don't understand is the package thing. So it's just basically saying a collection of libraries. So a bit like an engine, right? They're used together. But then that engine can be used for a game, which is another package, right? Okay, got it. Gotcha. Hey, thoughts right? Welcome. Glorious, how you doing? Not bad, not bad. Just trying to extend this code to work for, yeah, work for quad trees and yeah, just figuring it out really. Might take another look at the paper again because it's a bit, yeah, a bit confusing. Ooh. Yeah, how have you been, Glorious? Packages mainly true for distributions, so you don't need a ton of packages. Right. Gotcha. I use Manjaro. because it's Arch Linux and you can set it up nice and easy. Comes pre-installed with a bunch of stuff, and you can just remove the stuff you don't want. But yeah, I've set up Arch tons of times. Just wanted something easier. But yeah, I don't really use much software. I just use NeoVim and Clang. Very nice. It's good. Arch is the way. Yeah. Three goes there. Yeah, I think we need to draw. I think we need to draw an overarching. Right, let's draw 16 more of these guys. 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And then I obviously draw 1. 2, 3, 4. So here's our quad tree. Now, realistically speaking, there's going to be another root node up here, or probably here, which is going to actually be 0. Right, this is 0. This. So internal node 1, 2. See, this is where I get confused with it. So this one will go 1, 2, and 3, 4. I don't know if it will be up there when the tree is this small. I think it will be more balanced looking, if you will. Well, so would that be 3, 4, 5, 6, 7, 8, 9, 10? Yeah, because these are siblings, so they have to be next to each other. So this would be 3, 4, 5, 6, 7, 8, 9, 10. So or realistically speaking, you might actually have, there'll technically be like a 7 and then an 8 node. Because I think they'll be next to each other in memory, but I don't know if this will affect how we lay out with this algorithm. Nine, 10, 11, 12. Now, right. But then this will then be 13, 14, 15, 16, 17, 18, 19, 20. Something feels off with this still. Yeah, I'm a bit confused. Maybe we should just build the tree as a binary tree and then convert that to a quad tree. Because I think this... Yeah, maybe we'll just do that. And it has to have a Windows style taskbar because it looks like it. Okay. It's just KDE. I don't know why people think it's Windows, you know. It's just got a task, you know, bar at the bottom. In dev, Endeavorous OS. I think I've heard of that one. Trying to learn a level programming course. C is the worst, has the worst learning curve. I'm not sure. Um, what are you finding difficult about C? Is it pointers? Like, what's the difficult bit? Or is it setting up a build system? Hey, Cat Payne, how's it going? Yeah, I've been away. I went to work and partied hard. So, and also been fixing my wife's MOT car, polishing off the lights, making them shine again. So, what part didn't you understand about pointers? Like, what's the thing that's difficult about pointers? Is it understanding what they are, or is it trying to not segfault and kill the program? Like, what part is it that you're stuck on? Right. So I think why don't we just restart this and just say we'll implement the algorithm to use with a binary tree because I don't think or our main contribution is an in-place algorithm for constructing binary radix trees. Right. So I think it says awk trees in here as well. Maybe if I read through the paper a bit. In this paper, we produce the fast method for constructing BVH's awk trees. Right, it does awk trees as well. So KD trees. So the overall performance scales linearly with the number of available cores, and resulting data structure is always in a strict depth first order. We start by presenting a novel in-place algorithm for constructing binary radix trees in a fully parallel fashion, and then show how the algorithm can be used as a building block for effectively constructing other types of trees. Right, so I guess I didn't read that section then. Because I read all of this. Right, BVH is octrees, KD trees, right. So maybe I didn't read this. Well, this is the comparison of this. Maybe read this and see how we understand it. More Bullish is an esoteric language. Took a look through just an iteration, generate sequence of hello world. Huh. I've never heard of that language. We'll link you to the paper, sure thing. I didn't link it earlier, but there we go. How's it going, Cat Payne? How you been? How's the wife doing? Following in the footsteps of some person who I won't bother butchering his name, we construct BVH for a set of 3D primitives as follows, using Morton codes. I was trying to say curves, but anyway. Morton code for each primitive according to its centroid. Right, it's the center of the thing, I imagine. Maybe. Sort the Morton codes. right? We've done that bit. Construct a binary radix tree and assign a bounding box for each internal node. We can contribute steps 3 to 4, right? Obviously, this is the binary radix tree, but we don't want it to be a binary radix tree. If the Morton codes for all parameters are unique, it's easy to see the binary radix tree is identical in structure to the corresponding linear BVH. Identifying the common prefixes between the Morton codes is equivalent to bucketing the primitives recursively according to each bit. Yeah. The case of duplicate Morton codes has to be handled explicitly since our construction algorithm relies on the keys being unique. This is something else we have to handle. We can accomplish this by argumenting each key with a bit representation of its index. So key tick equals key something I, where something indicates the string concatenation. So concatenation. That's not nice. That's not a good solution. Yeah, it's not a good solution. Because you're basically saying, hey, take a 32-bit integer and just put another 32-bit integer on the end. So we've got to look into, anyway. In practice, there is no need to actually store the argument to keys. It is enough to simply use I and j as fallback if I equal to j, then evaluating. So what it's saying is, in practice, it's best not to just concatenate it, because if they're the same, you just switch to using the index instead. Okay. Right, that makes a lot more sense. Yeah. Cool. Previous methods of linear BVH calculate the bounding boxes sequentially in a bottom-up fashion, relying on the fact that the set of nodes located in each level is known prior. We adopt a different approach where the paths from the leaf nodes to the root nodes are processed in parallel. Each thread starts from the leaf node, walks up the tree using parallel pointers, and we record during radix tree construction. We track how many threads have visited each node using atomic counters. The first thread terminates immediately, while the second gets to process the node, and obviously it continues up the tree. So this is what we actually implemented before in the past, but we didn't do the other part of it with this complex searching. Yeah, so basically, if this is a binary tree, this one goes, they both increment an atomic counter in the parent node, and the one that incremented it last is the one that carries on and goes up the tree again. But while it's here, it calculates the bounding box around these guys and then stores the result in there. So that's all that's talking about. That's the step after the step we're doing right now. Right, octrees. Here we go. To construct an octree for a set of points, so we want a quad tree, we observe that each 3k bit prefix, right? So initially it's a 1-bit prefix. So I'm guessing we use a 2-bit prefix for our 4 tree. This is saying 3-bit. So that's what I was thinking, but it didn't end up working. Of the Morton code maps directly to a octree node at level K. Yes. We can enumerate these prefixes by looking at the edges of the corresponding binary radix tree. An edge connecting a parent. Wait, we can enumerate these prefixes. Yeah. Each 3k prefix in this case. So if we run that code, What it's talking about is, this is the Morton code. So what it's saying is usually you have each, this one here, if it's a binary tree, when it goes down, if like, this could be the bit that tells you to go left or right, basically. But for 4, you got these 2 bits which can tell you 0, 1, 2, or 3. But it can skip them sometimes as well. Like, these all went down 0, which doesn't make any sense. Yeah, maybe that's the problem, is I was making it like an odd. I was removing the odd bit. So I was always making the count leading zeros even. Maybe that's slightly wrong. We can enumerate these prefixes by looking at the edges of the corresponding binary radix tree, an edge connecting a parent with a prefix of its length. Parent. Right. Good man, wife is good, work is good, can't complain much. Saved 10k since April. Pretty good, man. Or dollars, yeah. Awesome. That's good stuff. Glad to hear, my friend. Got any ideas what you're gonna do with that money is? Because I know you're planning on a child. Are you saving for the baby, or are you planning on going away, buying a car? What's the plan? Yeah, invest, saving for a house. Awesome, nice. Family car, lol, lots of things eventually. I know, right? Yeah, for me right now, we're trying to recoup savings back again. So we went on a holiday to Australia. We had a good time. But yeah, we're currently feeling the yeah, trying to pay back some of that credit card still, but it's going. It's good. But yeah, I hope you start saving soon again. Everything in the shops is just so damn expensive these days. Like, food shop is massive. Just going out anywhere and buying fast food now, or anything, right? Just the price is just extortionate these days. It's crazy. Put down a Porsche 718 down payment. Is that like a really old Porsche or something? I haven't even known that much since April. I know, right? These rents and these supermarkets. It's crazy, man. Right. So we can enumerate these prefixes by looking at the edges of the corresponding binary tree. An edge connecting a parent with a prefix of length. This parent. So this was a little function. These papers like doing this, but it had 2 parameters before. Oh, count leading zeros. By computing the XOR between the 2 keys, count leading zeros. Yeah. Right, counting zeros of parent. It's referenced up here. We can find it again. Oh my days. Right. using this to denote the length of the longest common prefix between these two keys. Longest common prefix between two keys. What happens if it's just singular? You know, I guess it's just saying run count leading zeros on it. Ah, this is saying this min. Maybe it's a result of something else. Why are papers so damn cryptic? Just punch out code and do a presentation. That's what it gets turned into anyway, isn't it? So silly. Right, maybe it's just a way of calling it another variable. That's probably what it's trying to say. It's another variable. An edge connecting the parent with a prefix of length, you know, squiggly parent to a child with prefix of length, squiggly child, representing all prefixes of length, squiggly parent plus 1, bunch of dots for some reason, well, comma, dot, 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 comma, right, so everything in between, or plus 1, everything in between, child. Out of these, squiggly child divided by 3, take squiggly child divided by 3. So that's 3 bits. I guess that's because of the 3 bits. R divisible by 3. We evaluate these counts during radix tree construction and then perform a parallel prefix sum to calculate the octree nodes. The parents of the octrees can be found by looking at the intermediate ancestors of each radix tree node. Yeah, so basically this is what we was thinking of doing, is just building the binary tree. Right, obviously I didn't think about this. That's the next step, but building the radix tree first. Sorry, the binary tree first, and then just turning it into a quad tree, right? Um, hmm. Yeah, well, yeah, well, I don't know. Yeah, we have that vote, isn't it, on Wednesday? But it's just politics, isn't it? It's just all, not sure how it end up. Um, right. We evaluate these counts during the radix, per, right. The processing thus consists of several steps. Calculate the Morse codes for these points. Sort the Morse codes, yep. Identify duplicates, i.e. points falling in the same leaf, by comparing each of the adjacent Morse codes. Remove the duplicates using parallel compaction. What? When did it say remove them? Anyway. Construct a binary radix tree. Perform parallel prefix sums to calculate the octree nodes. Find... Right. Okay. Right. Yeah, so I think we can just... Okay, I get the idea now. So the idea is we basically just make it work. So produce a binary tree first, then produce a quad tree from that. So effectively what we would like to do is change this drawing code to also work for, so we'll look for these magical fours. I think there's only one magical four. Children cap, let's call it that. So where we got that magical four? Children cap. So we'll just, so the basic idea is for now, just throw a 2 in there. And let's just see how, hang on a minute. Yeah. So does it just, right, they kind of went off screen a bit there. Right, that's yeah. So drew it, okay. It's just the way we attached the nodes. Right, so you start from the number internal. So this is the number of internal nodes for a quad tree. And then for a binary tree, it is just take 1. So basically, I randomly generate all those there. Where's the code where it links up all the child nodes and that? Alright, that's internal nodes. Here it is. Yeah, so we'll find that magic 4. Alright, so let's see how that looks. Right, so here's a binary tree now. This one is obviously hard-coded, but we can now play about with the algorithm again. So this is the algorithm. I need to get it right. So I did kind of mess around with this a bit. So that'll be internal node equals index, or leaf node index, internal node index, and then this diff thing needs to be corrected again. So if R delta L delta 1 minus 1. I think that's all I changed. Oh, and I changed this to 4, wasn't it? Right, so that should produce, fingers crossed. Yeah, it's a bit wrong. Look into that. See if I got it right. As reform take over, it can become better in terms of trans rights, which is all I already care about, but as an immigrant, what Brits love to call expats. Yeah, I don't know. I think Labour's going to win, but you know, you just gotta wait and see, because it's always, Conservatives and Labour And, you know, the system basically sucks. Anyway. Honestly, it would just be better if there's just no parties at all. Because if you take a look at parties, everyone in the party does not agree on everything the party stands for. And it would be better if it was just people that were elected that individually had their own thoughts and then they passed laws, you know. It seems very weird having parties that take a whole bunch of issues into one group of people, and then it just becomes a two-sided battle. Whereas realistically, each problem is a two-sided battle, right? Basically. That's more of a thought of using the first past the post system. I'm not sure what that is. First past the post. Former British colonies tend to use the voting system. Right, yeah, vote for a single candidate, right? So you basically end up having to play the game, isn't it? Where, oh, well, you didn't waste a vote if you vote for this person, right? Is this what it is? Cast a vote for a single candidate. The candidate with the most votes wins. Yeah. Well, I don't know if that's part of the that's it's kind of irrelevant to what I was saying, but yeah. The problem is that the candidates, in my opinion, belong to a party. Like parties just shouldn't exist. Like there should be a candidate who has ideas. He has his own ideas, or he or she, whatever, right? Have their own ideas on things, right? Each candidate should run. You elect a candidate in your area, and then that person will fight for those ideas. That's it. I don't think having a party that stands for a bunch of ideas makes any sense. It just seems very strange and bizarre. That you have to pick a party for a collection of ideas. Um right, what are we trying to figure out now? Yeah, so I want to see like compare my code to this code to see what did I do? What am I doing? Did I change something else and mess something else up? Don't think so. Right. Yeah. Right, so why? Right, so why are my range numbers a bit? You know, maybe they're fine. So your leaf node 1. So let's do the 8 one for a minute. 8. That's 8 in it. Good. Right, 0 to 1, 2 to 7. And 3 spans 2 to 3. Right, so ones that only span 2 nodes, that's fine. Hmm. Yeah, maybe this is fine. It's obviously going to be in a different configuration too. Because I think this one here, 4 and 2, are the most parent ones. Whereas the other ones are more. Yeah, so let's now write the rest of the code that links the tree up. This just determines the range. So I think this is 2 here, 2 to 7, 0, 1, 2, all the way to 7. Three, four, five, six, seven. Ugh. That must be. Yeah, no, still feels a bit off. Still feels a little off. Well, that's a perfect system to not be able to create a government. Just look at the Belgium or the Netherlands, which have a ton of parties and without party, everyone is in a way its own party. So you need to negotiate with at least 351 people individually to form the UK government, right? Essentially, that's why you have less people, maybe. Like, ideally, yeah, you would need less people. Yeah, so obviously the tree means that. So this. Yes, the 4 node one worked fine by the looks of it. That ranges thing is fine. So we could write the next piece of code at least. So after determine range, you need to then select the 2 nodes. Where is it? Yeah, so you need to do this find split thing. So there's another function called find split, which does another binary search and basically finds where these dots get placed on that range. So the range is this bar, and that red dot is where to put the split effectively. So this will be. So this will split between 0 and 1. This splits between 1 and 2, but 1 and 2 internal nodes. This is between 0 and 1 leaf nodes. So yeah, we need to find. There's a bit of code to do that, which is here. So the split function itself doesn't tell you where to either split the internal node or the leaf node. That is done with a bit of logic afterwards. So they call it gamma here. So this will be the index to the left node. So it'll be that plus 1. Then if it's equal to the min, then you need to use the convert it to a leaf node, basically. The left-hand side, and then if it's equal to max, you convert the right-hand side to a leaf node. So it's done afterwards. So we'll put the other function in here. I'll do another loop. I'll break from. Right, so first and last ends up going in, that's the range. Then number of objects. On leaves. Right, so first and last would just be range.x, range.y. Leaf Morton codes. So this is saying get the middle basically, because range and start plus end divided by 2. So that'll be, they call it gamma, but yeah, it's the split location. Right, different signs. Right, so and split. All right. So that gives us split location, and then we need to marry up the nodes from here. So it's just this code here. So given, we should really take this index and call it internal node index. Hey RCT, no, I just tried doing this code to work for the four-way tree or the quad tree, but we couldn't quite get it to work. And then I read through the paper a bit more, because I read up to this part here, but then if you keep reading a bit further, it does mention how they get it working with octrees. And the way they suggest doing it is by building the binary tree first and then calculating the octree from that one. So we're just gonna do a version of that basically. Yeah. So yeah, it kind of sucks. It has to have an extra pass, but hey. But yeah, how's things been, RCT? How you been? So this should be the split position. So I guess we'll just grab this code here and just try and hook up the tree perhaps. And then maybe uncomment the other code as well. Yeah, should be good. Should be good. So gamma is split. Num objects is num leaves. Crap. Leaves count. Right. So index would be internal index. And self nodes would be just nodes, isn't it? I think so. Yeah, it's just nodes. Right, so they have like a left and a right index. So for us, I would like to put those next to each other in memory. So obviously that's not possible when it comes to building the first tree. But so perhaps we do need a left and right node, but this is fine because what I would like to do on GPU is have them next to each other in memory. Yeah, just be better. So have children indices instead. You'll have up to 4 of those in this debug view thing. But yeah, on GPU, I want to squish them close to each other, next to each other though. So children start index. So it's gonna do right. So just be children indices. Yeah. Right. So this builds a quick and easy tree. We could disable this code. But we can always bring it back. So this is the code that's going to build it properly. Children indices 0, 1. I don't know what this thrust thing is, but AO. Children indices. So we store our leaf nodes after the internal nodes. Yes, correct. So it's the same as this one. And then the parent is equal to this internal node. Parent plus 1 we call it. Just so 0 is null. Yeah, so let's see how that hooks up. We are going to draw the tree. So if the tree comes out correct, then the code is correct. Because now we'll put the actual code in. Right, so clearly we're buggered summing up. Yes, they worked. So the one to look at so let's bring it down to something simple and see what happens. So this should be happening, I think. 0 to 3, yeah, so we should be seeing something here. So we're going to print out Yeah, thrust. Bit of a weird name. It's got the word rust in it, so it thinks it's a language. Perhaps that's... I think we just found the name for your new... So instead of Rust, Mr. Jomaga, or Miss Jomaga now, you should call your new language Thrust. What do you reckon? It's like... Depends how Rust-like your language is going to be. Nah. Alright. Have you got a name for it? Yeah. I don't know what I buggered up. Hey, you know? Zinc oxide. Ooh. The name's a hard, plus it needs to be Googleable. Right. Yeah. Well, it's fine. Here's me make it. You say thrust lang. You know, be like go lang. You know. That's all right. Ugh. So I don't know why. So what we can do is we can just print out all of the bells and whistles. So what we actually want to say is like, so for this internal node, what are the children that it has? I think. Right, 1 and 2, 3 and 4, 5 and 6. Why don't I see no tree? I expected to see a tree. Because obviously, links to 3 and 4. 4 is where our leaf node starts. 1 and 2. So internal nodes 1 and 2. 3 and 3 is where the internal node would start. So the leaf nodes would start. These are 2 leaves. Yeah. So why aren't we seeing... What is this thing? Right, root is start. Root is 0, yeah. Easy. So, alright. Core breakpoint, and we go. Ding. So, what did I do that's so silly? So, right, I didn't set the children count. For crying out loud. I did think about that when I was writing the code. When I was writing these children indices. So if... You saying everything has 2 children? It can't be right. So I think what you would like to say is if they are not equal, then it's equal to 2, if not 0. I think that's the logic. But let's roll that for a bit. Right, so that looks like a binary tree. Looks a bit odd though. Seems to be building though in a very... Right, so I think... Right, so it could possibly be correct. But what's happening is there's more children now. There's more depth than it was when I built it in a very basic way. So I think the other one ended here at this level, but this one kept going, so therefore these are looking more squished. Right. But yeah, you're only getting 2 nodes. The question is basically, for this to be correct, we have to be able to visit all leaf nodes. All nodes. So the way we can guarantee that is if we have a global. That's how you solve all problems. So there's an array of nodes somewhere. So we just have a boolean and we say has visited. And I forget the exact number of nodes that we have, but it's somewhere. 256, I was thinking that number. So we just put that there, and effectively, we just want to... You got a node index, and you go boolean. So you say has visited node index equal true. So the plan is, right, before you kick this off, you memset, or you do a 0 array, which does a memset basically over the whole array. And the next thing to check is that are all of the bits or all of the booleans set. So we go over all of the actual nodes. So we go index 0 internal plus leaf nodes, and we're just going to do a nice assert, and we'll just say assert that has visited index. So if this never fails, and we'll, then we can celebrate. Right, it seems all right. I think we've got to double check other numbers, but let's we can monkey around with something. What should we do? Let's make it so, I don't know. Right, let's just not set the boolean. Let's just make sure the assert actually triggers, right? Right, the assert triggers. Okay, so it seems like we're building the binary tree correctly. I do want to double check the number of nodes. We are printing. Let's double check something. Right, let's comment that out. So I think we print out the number of leaves. So I just want to double check those numbers quick. So 64 leaves, 63 internal nodes. So that should give you a total of, 127, right? Quick maths. Yes, there's 127 nodes here. Okay. So the thing we have to double check is what happens if you get a duplicate Morton code. We haven't handled that case. So that's the other thing that we didn't handle. So if you get a duplicate, yeah, so what about, did I get this right? If I say these are always equal to 2, that's going to be a problem, right? No? Okay. How do we know if it's a leaf? How does it know when to stop? Because you just go here and you just keep going. Thought that would have... So I guess the question... Oh no, because it's an internal. The leaf nodes never compute... Yeah. So the internal nodes... Huh. I don't know if they ever link to the same thing. Maybe that's not needed. So the internal nodes always link to 2 things. Yeah, that's true. Right, that's fine. That's fine. Okay. So the next thing to solve is what happens if you have a duplicate key. So how do we make a duplicate key? Well, we've got that more encode thing that we generate randomly. So all we have to do is just do this, right? 1 or more encode 42 is equal to 77. So we're making a duplicate. Does it all fall apart? So the thing is, is that we need to keep things simple. So why don't we say node 4 is equal to whatever 12 is, and we'll be able to see this. So they should show up next to each other. So if we only have let's say 16 leaf nodes. Maybe it's, it's really annoying how they go off the page. Right, let's do it even less. Let's just say, like, you know what, 0 is equal to 1, and that way we only need a small tree. Right, so we've got 4 nodes. So there should be a duplicate here. Here's the duplicate. Right, that seems to have worked. So my question now is, so this is different. So what happens if we have 3 duplicates? So let's make 2 equal to 1 as well. And we'll have more node. Oh, we're gonna assert. What? Don't I get back traces and things? Where's my call stack? Right. So it seems like we got in an infinite loop. So that's obviously a problem to fix. So the way they said they solved that problem in the paper is they said, so this is the juicy bit. We accomplish this by our, right. The case of duplicate Morton codes has to be handled explicitly, since our construction algorithm relies on the keys being unique. We accomplish this by argumenting each key with a bit representation of its index. Sorry, augmenting each key. So it's basically saying take a key and then concatenate the index on there. So this obviously means you can concatenate a 32-bit integer with another 32-bit integer, making a 64-bit integer. But, you know, they make a good insight here, which is kind of obvious in retrospect. In practice, there is no need to actually store the augmented keys. It is enough to simply use I and J as fallback if the two keys are equal to each other. So, when evaluating this thingy, squiggly IJ as we call it. So for squiggly IJ, see this has probably got a name, it's probably some Greek there in it. What have I done? Delta, right. Yeah, it's funny. Delta. So this means that right. Anytime you do this common upper bits, right, you effectively just so anytime you do this, when these two codes are the same, you've got to use a different, you use the indexes instead. That's all it is. So, or you always make sure they're unique. That's the other thing. So if we position things in 3D space, we can always... See you, Jamega. Good to see you. Have a good rest of your week if I don't see you. So we can either introduce inside the shader a bit of conditional logic to say, hey, if these two things equal, then, you know, use then swap out the Morton codes for the indices of the leaf nodes instead. Or the other solution is to change the Morton codes such that they are unique. Such that they are unique. See, doing that on the GPU is quite difficult. It is possible. No, it's probably quite bad. Because each thread depends on the previous thread. It's just terrible. But we probably only have to do that when because the basic idea, right, is that you build these ellipsoid models in the editor, and so the editor just has to produce when you save the file or whatever And like, so the BVH could just be constructed in the editor. So the speed isn't necessarily, well, yeah, it needs to be constructed in, the speed is kind of required, but yeah, I think we can do the branching for now. Maybe. Wait, did I want to build it? Yeah, I still need to build a BVH per frame. I still need to build a BVH per frame as well. Yeah, making those unique on the GPU is just difficult. So I think we'll opt for the branching. Or maybe they can be select instructions. So I guess we could try that. So you effectively want to so it's IJ instead, and then the idea. Leaf node more codes. So you then figure out how do I get AB. So if if A equal B, I guess then A is equal to I. I think that's the way you solve it. Yeah. So we just got to change this around a bit. So instead, oh boy. Oh, the baby's awake. 2 minutes. I'm just gonna go and see my wife's back. Yobby. Alright, hello everyone, welcome back. Yeah. Right. So yeah, we're just sorting out this, we're passing in the array instead. And rather than passing in the codes, we're just passing in the indices, and the function should handle yeah. The function should handle the the key duplication thing, which is pretty neat. Yeah, I do want to maybe range X, range Y. And then first code, middle. Range X, then middle. Right, so we tried that. We've got 3 duplicate keys. It was crashing, so this should fix it. No. Still got a crash. So not all of them are visited now. Let's double check that. If one codes are all unique, it's easy for its tree to identify. Sorry. Identifying the common prefixes between mock codes is equivalent to bucketing the primitives recursively according to each bit. The case of duplicate Morton codes has to be handled explicitly since our construction algorithm relies on keys being unique. Hmm. Hmm. Hey, Swingfunk. Just an algorithm to. It's an algorithm to construct a binary tree on GPU. In a highly parallel way. So, yeah, it's okay. We have it working. It's just when we have duplicate keys, it crashes. So yeah, it doesn't work. So I'm just trying to resolve it now. Although yeah. So let's put this back. Let's make this not trigger. That should be the same. I want to then remove the duplicated keys. So these are duplicate keys, let's just remove those. Yeah, the ultimate plan is to build a quad tree. The issue is we need to build the binary tree first and then get the quad tree from the binary tree. So this still works. See, after sorting all of your nodes, your duplicates will be next to each other. So ideally you just check to the left and to the right of you. And I guess you just need to keep doing that and incrementing the right hand side one, if you will, until you never, until they're not equal. But it's a lot of it doesn't seem like the so you could launch like all your threads over every single node and just put it in a loop and do an atomic read and write, basically, and keep upping it until could you? No, it doesn't seem right. Seems like it'd be problematic. You might have to do it in steps. But yeah, so the answer is basically remove the duplicates, or so they say here about doing that concatenation thing, which we've just tried and it didn't work. It seems to be crashing. But then they say here in these steps, 3, identify duplicates, points falling within the same leaf node by comparing each of the adjacent Morton codes. 4, remove duplicates using parallel compaction. So this is like a strategy we could apply. I don't know what parallel compaction is, but it sounds like a GPU thing. Parallel compaction GPU. Have they not got a reference for that? Also apply the idea of using mock codes and constructing octrees in the context of surface reconstruction instead of generating a hierarchy from top down. Series of parallel construction. Sorry. They start with the leaf nodes and perform a series of parallel compaction operations to determine their ancestors. Yeah, I don't know what it means by parallel compaction. Right, how does this blog say about duplicate keys? Yeah, so this is saying this numbering scheme never results in any duplicates or gaps. What they're saying is when it's linking the nodes, it never links to the same node or creates gaps. It's not saying duplicate Morton codes. I don't think... Yeah, I think this blog skips over that issue. Stream compaction, what does this do? Yes, a scan is like a prefix sum, but across a whole array. I don't know what stream compaction is. And is that the same as parallel compaction? The main focus of this project is implementing stream compaction and other parallel algorithms in CUDA, which is widely used for important accelerating path traces and algorithmic thinking. Implement stream compaction. I'm still not sure what it is. Right, produces a smaller array which contains the indices. See, if compaction means remove, because that's what it's kind of sounding like, that doesn't make any sense for us because, and I don't think for them either. So, right, if you have your one ellipsoid, which is what we're trying to build a BVH, right? One ellipsoid and then another ellipsoid, but you're using the center position to know whether, and that's the Morton code you're going to give them, and they end up getting the same Morton code. Well, you still want both to be there in the BVH. So removing them is probably not a good idea. And I think it's removing it. So yeah, I guess that's the other option. You either remove it or you somehow make them unique. Ah, I just realized. They're saying it's as if it's like concatenating two. Right, I get it now. So if they're identical, this count leading zeros, they're all going to be the same for the first 32, isn't it? So I think basically we need to add so how many of the bits are the same? Right, so we need to add 32 on it. If is same, so we can optimize this code in a bit, we just need to get it to work. Count plus equal 32. Right. So I think that could be the logic we're missing, but I'm not sure if it goes above 32, is it? Yeah, something to be aware about. Right, that could be okay. So we've got three duplicate nodes now. Right, it still crashes. This time it's on this one here. on has visited. They've not all been visited. So let's take a look at what tree gets constructed at least. Let's remove that assertion. Right, so if we do that small tree again, you've got a couple of 6s. So 0. So you got 4 leaves. Yeah, we're getting duplicate. Right. So I think, yeah, so it's getting duplicate. Right, so with these common up a bit things, I want to read that line one more time where it talks about the duplicates. In case of duplicate Morton codes, well, the case of duplicate Morton codes has to be handled explicitly since our construction algorithm relies on keys being unique. We accomplish this by augmenting each key with a bit representation of its index, where it's key concatenated I, where this indicates string concatenation. It just concatenates the bits. In practice, there is no need to actually store augmented keys. It's enough to simply use I and J as fallback. Well, we tried that and it didn't work. You know, one duplicate key seemed okay, but then when there was 2, it seemed a big problem. Sorry, yeah, when there was 2 duplicate keys, it was fine. But 3, I think there's a problem. So we tried to sort of simulate the concatenation by adding 32. And then we also just tried not doing that. And that results in infinite. Oh yeah, that results in recursion in the tree. So it just recursively goes around the hop again and again and again. Yeah, so I think our only other option is to actually make all of our keys unique, and that's okay. That's a solvable problem. It just means we have to write that in on the GPU, basically. So yeah, so I'm gonna undo all of this for a sec, because this was better the way it was before. All right. So the other solution is to just make all the key. We just got to ensure all the keys are unique. That's all we got to do. Right. So the next thing we'll have to do after this is somehow produce a quad tree from this binary tree. I've got ideas. The paper also has some ideas as well, even though but it's a bit difficult to understand what it means. So off stream, I'm going to try and figure out exactly what it's trying to say, how to produce an octree from this. But I've got an idea of how we could do it with a quad tree anyway. We've just got to join. We've just got to join 2 siblings together and produce a single. You just if you get rid of these two guys, right? You've got 4 children. Ta-da! So it's something like that. So we just have to produce another tree, which has 4 children instead of 2. Well, or 2 to 4 children. Yeah, it'd be something like that. Yeah, so good progress today. At least we got something working, which can be translated to GPU. But yeah, we didn't get the quad tree working yet. That'll be next time. So our next be on Thursday at 6:30 p.m. Wait, 7:30 p.m. GMT +1. And we'll yeah, there's a timeline. There's on Twitch if you want to check that out. A schedule. Yeah, I think there's a Discord if you want to come and hang out in the meantime. And I also stream Sundays as well if you want to catch me there too. But yeah, good progress. Good progress. Let's raid the old new guy. Alright, have a good Wednesday, and I'll see you all on Thursday, hopefully, if not Sunday. Rightio. See you.